Hi, my name is Wayne Green. I'm with the FS1 spectroscopy team. This is an SES collaboration that we've been doing using Zoom with people all around the world. Tony Rada in England, Jerry Foote over in Utah, as I think about the limits. Greg Jones up in Oregon, and Tom Smith down in Weed, New Mexico. So it's a wide geographic area. We meet roughly once a week, sometimes a little more frequently. And we discuss issues that we've uncovered over the last year with the with the low spec spectrograph. Principal one, of course, was thermal expansion and flexure, which Jerry Foote has addressed by using an aluminum extrusion. The other problems that we had is we began to carefully follow the light through the slit, through the collimating lens, onto the grating, off of the grating, off to the so-called camera lens to go onto the sensor. And in doing that, we discovered a number of things. We also looked at the problem of injecting a calibration light source and guaranteeing that the light lines fall in the same position on the sensor that your science lines coming in from the sky happen to fall there. So in that whole process, what we discovered was that over the course of a night, that you can see a shift in the spectral lines along the dispersion axis. Over a 1 hour period, Tony Rada took a series of FITS files, and the subtraction that you can see here shows that typical pattern of a negative going spike where essentially there's the dark part, one is subtracted from the other, and then a little contribution where they kind of got added together. Those are definitely red flags to us that say that we need to be taking calibration lamps images more frequently during the night. So in order to do that, the Kaizen ring came about. Greg Jones suggested it, and it consists of a circle that your science light flows through, does whatever it's going to do. And then we surround a surface back behind towards the spectrograph. We shine light towards this ring. The ring then goes into the spectrograph in such a way that it's conformal with the optical axis of the telescope and of the spectrograph, and also in such a way that there are no moving parts, it's easily repeatable, and we can turn them off and on by using simple microprocessor control languages or control commands. So one of the things that we had done in this whole thing is we noticed that we wanted a motor to focus the collimating lens. If the collimating lens isn't perfectly focused, you'll have either a diverging beam away from that lens or a converging beam away from that lens. In other words, really far field, really near field type of an effect. And that adds up to having a different angle of incidence for each ray that goes across the face of the grating. The grating equation tells us that the angle of diffraction is equal to a function of the angle of incidence. If the angle of incidence is held constant, then you get parallel or collimated light beams. So all the red beams will be parallel, all the blue beams will be parallel. Now they'll be in a different direction. That's the nature of diffraction. That's what we want. We want a dispersion axis. But what we don't want is we don't want the blue part being a little out of collimation, and we don't want the red part being a little bit out of collimation. And that results in having an out of focus collimating lens. So in order to help mitigate that, what we did is we added a little cam that moves our collimating lens about a millimeter and a half, and that compensates for the very extreme temperature swings that we can see. One of the key things that I wanted to focus on, just as sort of my contribution to this video, is the slit. Greg Jones has a scanning electron microscope at his disposal. He was able to make SEM micrographs of various slits. One of the slits is a laser cut slit that you see fairly inexpensively in a number of sources. It's about a 3 millimeter long slit, varying widths. Now, it looks ideal until you take a close look at it. And what we see is it looks like somebody went at it with a cutting torch. You know, I had that emotional reaction when I saw these SEMs. Intellectually, I expected what I saw, but just that visceral gut feeling that you see from all of these defects that are along these slit edges. Each of the defects, for example, the spalls, where the little pieces of metal stick up above the slit itself, ablation, where a little piece of the side of the slit exploded off during the cutting process. Each one of those introduces an artifact that affects the resolution of the spectrograph. It really affects the diffraction pattern that comes off of the slit. We also have a micrograph, as you can see, of the OVO slit. This really smooth light gray area is the glass surface. Now, an SEM does not see through glass, it sees the glass. So you can note it is a really nice and smooth texture, a very good metal deposition of the chromium material that they use to make that slit. That makes it an excellent choice for a slit. It's also a little bit longer, it's 6 millimeters long. The next thing we said, well, gee, the old days they used to make movable jaw slits, and would a razor blade, for example, be a good thing to use? And we all laugh about lashing up our first spectrographs using razor blades. Turns out that that's an excellent slit material, as these spectrographs will show you. Here's one of a box cutter. The box cutter has it's a used box cutter, so it's been beat up. But notice how it's so much smoother than the laser cut surface. A double-bladed razor or double-edged razor blade is an excellent source for a slit. They actually get sharper as they get warmer, and they're pretty sharp to begin with. They're also very, very, very consistent in how they come down. It's measured, as you can see by some of the numbers on this micrograph. So to close up about the slits, is that we are back to the drawing board on putting a new slit mechanism in one of these spectrographs in such a way that we get a good polished reflecting surface for Tony's guider to work with. And we also get a really well-made spectrograph just for general small telescope use. So again, this is Wayne Green with SAS, the FS1 spectroscopy team. And we'll turn you loose with the rest of the video. Thank you very much.
Hello, I'm Jerry Foote. I'm part of the FlexSpec team. Today I'd like to talk to you about two issues that we've been looking at, thermal stability and flexure. But first, let me step back a little bit and talk about where we came from. For about 2.5 years now, we've been working with Paul Gerlach's low-spec series of spectrographs. These are 3D printed DIY type spectrographs that is completely 3D printed and uses commercial optics to generate the spectrograph. It's a very compact unit. You can see there's a telescope port, there's a guide camera port, and then there's a final camera port for the science camera. This is how we started. What we went to next was we looked at that carefully and tried to determine what its shortcomings were, and we made some measurements. One of the first things we found is that the low spec suffers considerably from thermal expansion. If the temperature changes a few degrees, it's not much of an issue. But if you lived in the US desert Southwest, where it might change 20 degrees C per night during an observing run, then the flexure and the amount of thermal stability offered by the low spec can cause problems. In fact, we've measured almost 6 angstroms shift in calibration over a night's run. The way we've addressed this is to look at the basic configuration of the low spec and come up with a method of thermally stabilizing it. Our approach is to take the flex spec, or take the low spec, and put all of the components onto a solid single base of material that we could control the thermal stability of. This is the general layout of that looks like. Notice that the optical path is very similar to the low spec, where the light comes in from the left, goes through the ovoid slit over to a fold mirror, then down diagonally to a collimating lens, then finally onto the grating, and then up vertically through a camera lens and onto the science camera. Most materials change their dimension with temperature. A good example of that is this list of materials that are fairly common. Note the bottom two are common 3D printing materials, and the upper 4 are common structural materials. Also of note is that with PLA, which runs at about 88 times 10 to the minus 6 millimeters per millimeter per degree C, compare that with INVAR at 1.6, almost 2 orders of magnitude difference between these two materials. What we're proposing is to mount all of the components onto a base. And if we make that base out of a specific material, then we can control the thermal expansion of spectrograph. Here's an embodiment of what that would look like. Notice that all the parts, all still 3D printed, are mounted on one continuous base, thus holding their geometry with a change in temperature. An embodiment of this design is this. This is a mock-up of how the FlexSpec one will look. Notice the ovoid slit, the diagonal fold mirror, the collimating lens, the grating holder, and finally the camera lens, and then the science camera is on top. One of the issues with this is occasionally with temperature change, we still noticed there was a calibration change. We traced that to an issue in the low spec that uses a micrometer and an arm coming off the grating, and of course the housing that it's all mounted to. As the temperature changed, we noticed that micrometer and lever arm allowed the angle of the grating to change, affecting that 6 angstrom shift we saw in the calibration. To counteract this, we decided to go a different route. Rather than using Mullen arms and micrometer heads, we decided to use a geared system. This had the advantage of allowing us to motorize the grating for our remote operations. This shows a picture of the motorized gear system. There's a stepper motor with a gearbox on the bottom outside the case. There's a small pinion gear and then a main driven gear. Also notice we've retained the ability to swap out gratings by magnetically coupling them to the main driven gear. Thus you can change the grating line frequency by just changing out the grating. As with any geared system, one of the difficulties is backlash in the gear train. Since the stepper motor has gears and we have a pinion gear and a main driven gear, all have backlash. We've gotten around that by always approaching the angle we want of the grating from the same rotational direction. This eliminates the backlash completely. Notice also that these parts, except for the motor, are all 3D printed. Again, getting the simplicity of the low spec. Another issue we have found is with collimation. If the collimation is not spot on, you're going to have difficulty with a decreased resolution. The reason is, if the calibration is off, then you have either a diverging beam or a converging beam approaching the grating. This means that the alpha angle on the incoming beam on one side is different than the alpha angle of the beam coming in on the other side of the grating. We've decided that what we need to do in the FlexSpec is to motorize the position of that collimating lens. We've done this with a system like this. This shows again, a stepper motor attached to a cam, and the cam moves a slider back and forth so that the collimating lens will move about 1.5 millimeters. We found this is sufficient range to precisely calibrate the collimated lens. Moving on to flexure. If you think of the spectrograph mounted on the telescope, and on that spectrograph are a heavy science camera and only a slightly lighter guiding camera, and then if you think of all these attached to one point of the telescope, as the telescope moves throughout the sky or throughout the night, there's going to be a flexure based on the moment arms of those heavy camera weights. What we propose to do is to build an exoskeleton around the spectrograph. Our approach uses a 1/4 inch thick walled aluminum extrusion, extremely stiff, and this aluminum extrusion then will contain all of the masses of the spectrograph and allow the spectrograph components to float within this exoskeleton. An embodiment of that exoskeleton is this 3D printed version of that extrusion. Notice we have the camera port opening here, we have the telescope port, and we have the guide port. This is about 2.5 inches thick, and it's about the same size as the low spec when you compare the size differences. They're still about the same. So we remain compact like the low spec. We've improved thermal and flexural performance, and I think we're moving ahead with remote operation, having 2 of the functions remoted already. Thank you. I look forward to seeing some of your spectra. Take care.
To analyze the temperature effects on the low spec 2, I added 5 temperature sensors internal to the spectrometer. I used a neon light lamp as a calibration lamp so I could monitor the wavelengths. I started with the at room temperature and set the unit outside where it was cold and allowed it to drop to by about 30 degrees Fahrenheit. I sampled every 10 minutes so I could monitor the wavelength. There was a dramatic shift in both the wavelength and the focus. The wavelength shifted by about 15 to 20 pixels over the test. I built a insulated enclosure with a heating pad in it and a control system to control the temperature to about 70 degrees. I repeated the test. It took about 40 minutes for the unit to stabilize, but after that point, it only shifted by about 1 pixel for the rest of the test. There was a shift in the wavelength, but not in the focus. What could cause this? In a previous test, I had tested the sensitivity to the micrometer, which pushes on a lever arm to rotate the grating. Turns out it's very sensitive, and there was about a 23 pixel shift per tick on the micrometer. To address these 2 problems, we're going to use a gear-driven rotator on the grating versus a lever arm. To compensate for the temperature that was affecting the focus, we're going to change the material. Today, the low spec is made out of plastic, which has a temperature coefficient of about 60. If we went to an aluminum, it would be a temperature coefficient of about 20. If we had 1040 steel, it would be a coefficient of about 11.3. We're planning on making a plate out of Invar, which has a temperature coefficient of about 1.2. The Invar should take care of any change in the focus, and the rotating gear for the grating should take care of the lever arm problem.
Hi, my name's Tony Rodder. I'm a member of the FS1 Spectrograph team, and I'd like to show you some of the things we've been doing with the calibration unit that we've been developing to go along with the spectrograph. We started off in a very well-known and traditional way, if you like, by developing a box to sit in front of the spectrograph between the spectrograph and the telescope. It takes up about 35 millimeters of back focus. I'll address that in a moment. This unit has T2 interfaces front and back, sorry, M42 interfaces front and back. And this was just a development unit that we began the tests with, just to see what we could and couldn't do. And it's a very familiar format, or it should be. It has, in this case, a screen in the center. You can see it there, okay? And the screen has a pupil at the center. Now this one's mirrored. So obviously we tried different screens. Mirrored, which was the best results, reflective foil, and then we thought we'd try something that we didn't have to move out of the way. So we tried a microscope slide, and that's there. Now you can hardly see it because it's obviously transparent, but this sits in the optical path between the telescope and the spectrograph, and it doesn't move. So we thought that's a good idea. We don't have to build anything that moves, more reliable, all that kind of stuff. And that started us thinking, and you'll see where that goes in a moment. So this is a simple device. It has a power unit in the top. The bulbs sit behind, I don't know if you can see there, but the bulbs sit behind a screen at the top. There's no lenses, there's nothing focuses, it just hits the screen. And you'll notice that there is obviously a pupil. It's not a big screen. If I hold it like that, you'll see, if I hold it the right way around, you'll see that at 45 degrees it produces a circle. And that circle is to match the focal ratio of the telescope. So whatever focal ratio you have, you could have the screen to match. And what that does, it mimics the right focal ratio cone coming into the spectrograph. So although it's a Lambertian distribution spread from that disk, it still looks like the right size pupil to the spectrograph. And we thought we were onto something here. And it does work. It works extremely well. You can see the results in the paper. So that's what we started with. Something that A, moved, or B, didn't have to move. And then one of the team, Greg Jones, said, look, if you're not going to move something, how about making a disk? Now you can see the center of the disk is a cone. And again, it has a pupil at the center. So this sits in the light path. It doesn't interfere with it. The correct size aperture can be made to fit your scope's focal ratio. It doesn't have to move. You can leave it in situ. And this provides the screen for the calibration lamp and the Relco, or the flat lamp, sorry, the Relco calibration lamp and the flat lamp, whichever we choose. It comes along with a sister disc. I'll just drop it there and pick it up again. Now the back is baffled black. The front are where the bulbs are attached. So if you imagine the bulbs are fixed around the outside of the rim here, you might be able to see the holes for the wires to pass through. Now Greg has actually developed a printed circuit board to hold the circuits, to hold the bulbs on a circuit which is easily replaced and removed, obviously, and it sits in this ring. And this ring has its back to the telescope, and it sits like that. The ring illuminates the cone, and the cone is what the spectroscope sees. And this is what it looks like. I'll take these connectors off because they're not needed. There you go. That's what the telescope sees. And I'll let you see this running in a moment. In fact, I'll do it now. So here's the unit. That's the rear of the unit, and you can see it there, illuminated. That's what the scope sees. And if I flick, you see the neon bulb? So you can have both the neon bulb or the flat lamp illuminated on a disc in the optical, or just around the optical cone, concentrated on the flat. And it works beautifully. Now the results are in the paper, so be sure to check those out. So we thought, we know we're onto something useful here. A unit, it sits in same back focus, same 35mm, power in the top. Screen is actually now down here where the bulbs sit. Very, very compact. Apparently, according to some of the team, not compact enough. Can we use this idea and reduce the back focus requirement? Well, yeah, we can. Because if we take the screen and the reflector, and then place it in a tube, like so, we can choose the right depth of tube for the right illumination for the different cones, because you can change a different cone aperture to suit your focal ratio, and insert that into the front wall of the FS1 spectrograph. So it becomes even more compact. And this thing does work. It works very, very well. And with that, I'm going to show you some of the results now. Now you can look up all the results in the paper. I'm just going to show you a selection. Here's the first one. Nice, tight lines, symmetrical lines produced over the full wavelength. This was using a 600 grating. But those, if you were looking for a calibration frame and you were looking to use a Relco lamp, you'd be very, very happy to see that. The next slide is the actual flat lamps. Now this was just using grains of wheat, but we chose to overvolt them, to overdrive them, just to see if we can improve the blue. Now, I know there's not a great deal of signal down in the blue end, there never is, but if you look at the paper, you'll see that, well, we're experimenting with different LEDs to boost the blue end. But again, this is as good as, if not better, than dangling a bulb over the end of the telescope. And that's what we've been trying to avoid. If we're going to make this fully automated, we have to get something that is easily operated on the scope, or rather on the spectrograph. And finally, now I know this doesn't tell you much, but the results are in the paper, and if you look at them, we've calibrated this solar spectrum with the actual calibration lines, and this is absolutely bang on. So we know the calibration lamps work, and we know the methodology works. Now, just to let you know how accurate it is, that solar spectrum is produced. The resolution is around about 1800, and the RMS on the calibration just for a cubic is less than 0.1. So we're really happy with the way this is going. So just to leave you with some takeaway points on the final slide, we've tried 3 different methods to provide usable calibration and flat lamps. They all work. We've settled on the small disc, which, by the way, we've called the Kazin ring because we couldn't think of anything else. So if you hear people talking about the Kazin ring, this is what they mean. It's a simple design with no moving parts, and it means minimal maintenance, and it's easily automated. There's minimal loss of back focus. When this is installed in the front of the spectrograph, we're probably losing about 25 millimeters back focus, but that's easily catered for with most optical setups. And the work that we're doing is continuing in terms of the different bulbs we use, and we will further improve those results. So this has been a thorny issue that has plagued amateur spectroscopists for years, dangling the bulb over the end and asymmetric lines, that kind of thing. we think we've got a solution to address that. So I hope this has been helpful. Talk to you later about the guide unit, etc. Bye for now.
Hi, this is Clark Yeager, and I'm a member of the Flex Spec group, and I'd like to talk to you a little bit about the high voltage power supply to drive the Roco calibration lamp. Back then we had some requirements that we wanted to see on the high voltage power supply. We wanted to have a high voltage power supply capable of driving a Roco calibration lamp. We also wanted to be able to turn it on and off with a logic signal. We also wanted to be able to turn on and off a flat lamp. And we also wanted to try to get some information about the orientation of the OTA. It was planned that this power supply then would be mounted on the OTA, and that would give us capability of getting an idea of what the orientation of the telescope is. And I'll get into that in a little bit. This is the schematic of the high voltage power supply. The heart of the power supply is really the high voltage section, which is, so you can see a little bit better. This is the high voltage section of the power supply. This was actually a modification from the power supply that was in the Richard Walker spectroscopy for amateur astronomers. There have been some minor changes made to it, but that's basically the circuit that was in his book. The heart of the power supply is really this 555 timer. It just puts out a square wave, relatively high frequency square wave that turns on and off this transistor. This transistor then drives a transformer that puts out a high voltage. You'll notice there's actually two transformers in here. There's really, the reason for that is availability. This transformer is available in Europe pretty readily, but not so much in the United States. So we chose a transformer here that's available in the United States. The layout is such that you can populate either this transformer or this transformer with no modifications to the layout, other than some component changes to adjust the maximum output. To turn this on and off with logic level, I put in a MOSFET down here that pulls this line to ground and turns the power supply on. The reason this particular FET was chosen is that it has a very low turn on, turn off voltage at the gate. And so it can be driven directly from a logic level. The second, well, this also was a prototype. And so I ended up building it up. And it turns out that we discovered that if for some reason the output was shorted, that this transistor could burn out. And so we made modifications to several of the boards to where we replaced this transistor with a MOSFET, and that dramatically improved that situation. The second thing that we were looking for was to be able to turn on and off a flat lamp. And again, I use a power MOSFET in here to pull this line to ground from a logic level. And so this line is pulled to ground. This turns on a flat lamp that's driven from a plus 12 volts. Now, like I said, this is a prototype, early prototype, and so conditions may change. But what we plan on is the wires then from the flat lamp and also the calibration lamp could be run along the OTA. And as I mentioned, the power supply would be mounted on the OTA. The other thing that we were looking at for the OTA was some sort of orientation information. So implemented a Arduino Nano 33 BLE Sense module. And in there, there's a 9-axis inertial movement unit, commonly known as an IMU. And this then can tell us a lot of information about how the telescope itself is oriented. This information can be passed back and forth to the Odroid through RxTX serial interface. This circuit was designed in KiCad, which is a free program that you can do the schematic capture, you can do the board layout, and so on, generate Gerber files to send off to have the board manufactured. KiCad is not a real easy program to use, but it does a very nice job. And I was able to define the physical dimensions of the board. I was able to do the schematic capture and do the component placement and board layout. The component placements, the wiring of the actual LAN patterns themselves, the solder mask, and everything that's needed to be able to manufacture this board. They do a really good job. I ended up sending them the information, and in one case, there was a minor error, and they caught that error, sent it back to me. I made the corrections and sent it back to them. Within 24 hours, the board is manufactured, and then it's dropped in the mail, and I received the boards within about 5 days. Place I sent it to is JLC PCB. It's a Chinese company, but they really do quite a high quality work. Another thing that's really amazing about them is the cost. They'll send you 5 boards for $2. And I actually ordered 10 boards for $5, but it costs $17 for shipping. And that's the reason I ordered 10 instead of just 5. But they did a really good job. I was very pleased with them. And so again, keep in mind that this is prototype stuff. Things have changed since I designed this power supply, and probably will continue to change some in the future. So things will have to be redesigned. But for right now, it's been doing a really good job. Well, thanks for listening, and have a good day.
Hello, I'm Tony. I'm a member of the FS1 Spectrograph team. And in this short session, I just want to give you an idea of what we've done with regards to a guide unit for the FS1. As you know, it's always been an area of difficulty for spectroscopists in terms of poor field of view, poor star images, indeed not being able to identify the target, and all that adds up to poor guiding. And obviously, if you're going to build a spectrograph, you've got to build it so that it's usable. So a guide unit is key. So what we thought we'd do is we'd look at all the problems that you get from guide units and try and put something in place that's usable. Indeed, that's flexible, that can be changed for telescopes of different focal length to obtain a good field of view, and something that's adjustable. So we started with this, and this is essentially the low spec guider. It has been changed considerably. You have the telescope port here. You have where the spectroscope would be is at this back end. Obviously, this is a standalone guider that we've been able to test. And you have the guide port here, okay? And it's where the guide camera would fit and the guide lenses. So we use this as a development platform. It's got a fastener and a focuser. But for the moment, there's 2 areas that I just want to draw your attention. We decided to keep the 3-way mirror, pick-off mirror adjuster. because that gives a very good adjustment range and allows you to steer the optical path for the guide camera. We thought this was critical. We retained it. We improved it a little with size and scope, travel, direction, that kind of thing. But that's something that we retained. The real change in this comes from the way the lenses are mounted. And if I just take away the guide camera for a moment. By the way, we used 2 cameras for the tests. One is this little low budget, I'll not call it cheap because it actually works quite well. It's a low budget camera, a little CMOS camera. You can pick them up on eBay for about $90, but very useful. And the other camera that we used for the images you're going to see was a standard Lodestar. So when you see these images, they've been gained by using pretty low-end cameras, nothing special. This is the lens holder. Now what we did, in order to get a good field of view for different telescope focal lengths, we decided to go for a range of lenses that sit in this nose piece. And we decided to go with 2 doublets. Now I know that's quite common. There's quite a few spectroscopists, astronomers around the world using that system, so there's nothing remarkable there. But if you imagine you can have any number of these with different focal length lenses here, which makes them easily interchangeable, easily customizable. And we tried 2 doublets, 50 millimeters a pair, 60. We actually tried a 65 and 70, and that gave us a range of fields for different telescopes. And we thought that was a useful development. And it also gives very nice, flat, clean view of the OVO disc. And that meant there was very little distortion in the actual image that the guider sees. So quite simple, goes in there, and the whole unit is then focusable. So and that's what it is. It's nothing earth-shattering. It's just something that's, we've taken a little bit of care setting it up and designing it. It's interchangeable. So we feel we've got a useful guider. What I want to do now is just show you 3 or 4 slides of the images we obtained, because we got something like, in the best images, something like a 24-minute by 16-minute field of view, and identified MAG 12 cameras with a 2-second guiding image. So we think we've done quite well. So first of all, this is CQ Gem, the first slide I want to show you. You can see very well formed stars even out to the edge of the image. You can see the asterism around CQ Gem is easily identifiable. And PhD2, the guide application we used, had no difficulty identifying guide stars and guiding. I'm going to show you the images in a moment. In the second slide, you can see a slightly larger field than the initial slide I just showed you. This is around the Messier 3 cluster. It's using a pair of 60mm doublet lenses with a 4-second Lodestar exposure. And bearing in mind, all these images I'm showing you was taken on a C925 telescope. We used a C-GEM mount, so everything's fairly low budget. But you can see that there's a good field of view, and there's there's loads of stars that you can pick for guiding there. And you can see from the from the right-hand side of the image, the full width of max of 3.4, those are good star images. The next slide I want to show you is an actual guiding slide image, and this is a guide star showing it's again the same 60mm doublet lenses, but these are 1 second lodestar exposures. And if you have a look at the track there across the bottom, we're looking at plus or minus 1 arc second guiding. Now my seeing in my part of the world is only about 3 arc seconds, so that's an extremely good guiding result. Again, no problem picking up a guide star. So the takeaway points I want to leave you with are that we've got an adjustable transfer mirror, customizable field of view using easily interchangeable lenses, a focuser for the camera, and we've achieved extremely good guiding images with a really good field of view. So for something that's run-of-the-mill and well known and well done, we're quite happy with that. We're happy bunnies. So I'm going to leave you with that. Thank you very much for watching.